Good idea for this question is just to start with the smallest values of n and see if we can make it work. So if n equals 1, then we've got the first three n positive integers. That's going to be 1, 2, and 3. And we're trying to divide them into three groups which have the same sum. Well, this is not going to be possible. So immediately we found a situation where it won't work. Let's take a look at n equals 2. Then 3n will become 6, so we'll have 1 to 6. And now this is possible because I could have, or in fact, I could add them up and divide by 3, which will give 21. And 21 divided by 3 is 7. So this is going to work. I'm going to need to put them in groups of 7. In fact, there's only one way to do this. I could have 1 and 6, 2 and 5, and then 3 and 4. So possible. Let's take a look at n equals 3. Now we've got 1 to 9. Okay, if I add these up, well, I've already got 21 from the first six, and then I'm just going to be adding another 15, 24. So it'd be 45 divided by 3 to give 15. So if this is going to work, then I need to make groups that add to 15. And in fact, there's a few different ways to do this. We could do 1, 5, and 9, then 2, 7, and 6, and 3, 4, and 8. So this is possible as well. In fact, there's more than one way to do it. You could do 1, 2, 3, 4, 5. They don't have to all have the same number in each group. 6 and 9, and 7 and 8. This question is not about how many ways we can do it, but I'm just illustrating we can do it in more than one way. Now, you can carry on going, but the thing is, we're trying to show which n it's possible for. So it might give you some insight, and it will work for n equals 4 and n equals 5. It'll just get, you just have to take some time to create the groups for each of them. I'm not going to show that here because instead we do need at some point to have a strategy to show which n it's true for. Even if you manage to get it true for 2, 3, 4, 5, 6, 7, 8, 9, 10, and you might think, well, it's true for all n, you still need to prove it because there's plenty of theorems in maths which seem to work for a long period, but then like fail at a much later point. Um, sometimes it's not obvious like why until you find the counterexample. So this is what I'm going to do, and I'm going to actually use this is what the solutions do, and it's quite an advanced idea, but it essentially is a principle behind something called proof by induction. I'm going to assume that it's going to be possible for n equals m. So some value. Therefore, we can split the first three m integers into three groups. And what I'm going to look at now is look at n equal to m plus 2. 2 more than that. So we now have 1 to 3m, but then also 3 times m plus 2 will equal 3m plus 6. So we also have 3m plus 1, 3m plus 2, plus 3, plus 4, plus 5, and plus 6. So what I'm saying is that we can definitely put these into three groups. And so let's just say I've got my group 1 here, group 2, group 3. But look what we can now do. We can actually pair up the 3m plus 1 and the 3m plus 6, a bit like I paired up 1 and 6 for that n equals 2. And that will give me 6m plus 7. So I can compare the new numbers. So they sum to 6m plus 7. And I've got my group 1, and I can simply put 3m plus 1 and 3m plus 6 with it. I can put 3m plus 2 and 3m plus 5 in this one, and then 3m plus 3 and 3m plus 4 in this one. Before I move on, I just want to justify this a little bit more. So we know it's true for n equals 2, and I managed to have my group 1 as 1, 6, for example, then 2 and 5, and then 3 and 4. So if I go with n equals 4, then I now get 3 times 4 is 12. So I've got these new numbers. I've got 7, 8, 9, 10, 11, and 12. But what I'm saying is that I can group the 7 with the 12 and put it into group 1, and then the 8 with the 11, and then the 9 with the 10. And I'm just adding 19 to each group. So because the sums were equal at the beginning, if I simply come along and add these new 6 numbers but pair them up so that their sums are the same, 19 in this case, then I will still have 3 groups that have the same sum. That's what I was trying to explain here. I was just saying it's true if it's true for n equals m. By the way, we've not shown that exactly because we know for some n it's not true for, but we'll come back to that. If it's true for n equals m and we can split them into 3 groups, then here we go. Here's group 1, group 2, and group 3. Sorry, I forgot to say 3. Now I've got these new numbers when I look at n equals m plus 2, but I can pair them up so they add to 6m plus 7. And therefore, because the sum were equal beforehand, then it's just going to remain equal. And what we've therefore shown is that, therefore, if true for n equals m, then it is also true for n equals m plus 2. But here's the thing. We know it is true for n equals 2 because I did that at the start. So 2 implies that it's true for 4 using this first statement, and then it must be true for 6, and then for 8, and I can generate all the even numbers. And we also know it's true for 3 because we did that one as well. So 3 implies 5, which implies 7, which implies 9. And this is the idea of proof by induction. It's like setting off some dominoes. As long as we know we've set off the first one, if the first one then we know knocks over the second one, sorry, knocks over the next one, then 1 will knock over 2, but 2 will knock over 3, and so on. It's actually a little bit more complicated because it's like 2 is knocking over 4, and then 4 is knocking over 6. We've got these, these pairs that are working, but it's still the same idea. So therefore, the property, and just let me remind you what the property was, the fact that we can write that for what integers of n can we divide the first 3n positive integers into 3 groups, each of which has the same sum. I'm not going to write that all down again, but the property is true for all n except n equals 1, where I showed that one was not possible. But so 1 doesn't, we can't, because 1 is not true, we can't say that then 1 implies 3. It's only if it is true that we can say it implies the next one. So all even and all odd except n equals 1? Very tough question because it's unlikely you would have seen this kind of method of proof before. So if you've come up with it yourself, then fair play. You know, it is actually quite an advanced method. It's not taught on A-level maths even. This comes into further maths A-level. But that doesn't mean that it's, beyond you to learn about it. It's just the fact that, yeah, assuming that something is true and that it then applies something else to be true. Here's the solutions and what they do. They do it in the same sort of way. I'd be interested to know if there's other methods that we could use to do this problem. So they bring in these extra numbers. They've stuck with n rather than m, and then they talk about them adding to 6n plus 7. It's just they write a few more words than I did. And then the different pairs they explain, and then the fact that we can add them to the groups and therefore get all these odd integers greater than 1 and the even integers. So it's just writing in words what I do with my diagrams, and therefore it's going to be true for all n greater than 1. Thanks for watching this. I hope you enjoyed this question. Well done.